is about molecular and ionic compound structure and properties. First of all, we're talking about types of chemical bonds, which when I first put all this together, I was like, we've already talked about all this stuff. Oh yeah, I haven't added in transitions or anything like that yet, so it's not done. Okay, a quick review of Coulomb's law. So remember, you don't have to use the specific terms Coulomb's law when describing things, but this is about why everything interacts with everything else. It all explains everything about the atom, okay? Where the protons in the nucleus will pull the electron from the outer shells towards it. And the more protons you have, the smaller the atom or the ion gets, okay? So some examples of this, of how it can differ, I have a couple in here and also in pictures. So this first one, I have the left picture is the sodium atom, and then the right is the sodium ion. So notice how it has the plus charge to show you that it lost one electron. But do you notice how the one electron, that is the valence electron for sodium, when it's lost, we don't have that ring anymore. We don't have that shell circle. And so automatically the ion is smaller than the original atom. Is that a good representation that maybe if you didn't understand that before, this picture is trying to show that to you? Maybe? I don't know. Because this was from last unit. Now, they're not exactly the same type of picture. I couldn't find it. But the left picture is sulfur and the right picture is chlorine. Which one is smaller? Which atom is smaller? Sulfur or chlorine? What do you think? Why would you say chlorine? Because it has more protons. Exactly. The number of valence electrons is different. So even though chlorine has one more proton and one more electron, chlorine is smaller because the extra electrons that get added are in the same energy level, the same area as the valence electrons for sulfur. And so because they're the same distance from the nucleus, it's not making it bigger because of that. It's in the same level, so the nucleus has more power to pull that level towards itself. Okay? So that's the kind of stuff that when we talk about periodic trends that you need to use as a base for your reasoning.
Wait, so which is bigger?
The smaller is chlorine.
Oh, okay, that makes sense.
Because it has more protons. So sulfur would be bigger, to answer your question. Sorry.
Yeah.
Yeah, so if you still need more help with that, let me know. But that kind of stuff we need to continue to use for our evidence to support our claims. Okay, we talked about electronegativity last chapter. Electronegativity values can help us predict whether a bond is nonpolar covalent, polar covalent, or ionic. The table can be found in your textbook on page 357. I think I pretty much have that number memorized now. And we wrote these, we scribbled these down because these weren't actually in your notes, but you wrote these down last unit. That the difference is, so when you take the values from the electronegativity table and you subtract them for the two atoms, when you subtract them, the difference can help you determine if it's nonpolar covalent, polar covalent, or metal, or ionic. That might supposed to be, I think it's supposed to be the word ionic, not metal, sorry. That's a typo. Change that in your notes. Okay. So now getting with electronegativity, and having polar covalent, we have something that's called a dipole moment. We briefly discussed this in Chem 1, briefly. A molecule such as hydrogen fluoride, which has a positive and negative side, is said to be dipolar or to have a dipole moment. So if we say that it's polar covalent, then that means that there has to be a dipole in that bond, okay? In these pictures, which I have a bunch more pictured for you, the red, does anybody want to take a guess? Is the red the negative side or the positive side? The negative side. So red is the negative side, and the blue is the positive side of the molecules. Whenever you see this coloring, I think, and there is coloring like this in your book, with these electrostatic potential diagrams, pages 358 through 361 in our textbook. where you might see more colors like that. But do you guys remember from chemistry 1, the slight charges? Yeah. So and we're gonna get in this chapter, it's at the end of the unit, but we'll draw our Lewis structures, remember, and that's how we can help determine, one way to determine if it's polar or not is from a Lewis structure, but the other way is from its electronegativity numbers. And if it is the positive side, that means that each atom on the positive side is slightly positive. Use the delta symbol for the slightly, and then plus or minus. But then we also have this thing that's an arrow. Okay, I don't think we talked about this in Chem 1. The arrow points toward the negative. Okay, so for this is a water molecule all the way through. The arrow here is pointing to the negative. And I always think about it that, like, you see how there's this other mark on the arrow? That's like the plus sign to show you the positive side, and then the arrow is pointing to the negative side. You could have just one general like this, or you could have like 2 arrows for a structure depending on how you're representing the overall polarity of it. If you're talking about a certain bond in between, then every single one will get its own arrow. But if in general you're just talking about polarity, then the one arrow for the whole molecule is fine too. So the arrow points towards the negative with these pictures. So I have some other ones here. NH3 is ammonia, not ammonium, ammonia. And so the nitrogen is more electronegative than the hydrogen. So that's why the nitrogen has the red at the top and the hydrogens are more blue at the bottom. And then for CO2, carbon dioxide, this one, both oxygens are negative. So do you see how it has the arrow pointing out for each one? So they're pointing to both oxygens in that case, not just to one. And then the carbon in the middle is the positive part. Okay? So for each of the following molecules, show the direction of the bond polarities and indicate which ones have a dipole moment out of the 4 listed. And then this table that I have up here, this is on the next page of notes. It didn't fit, so it's on page 2 in your notes. That helps. This table helps to see when there's a cancellation of polar bonds. And when you have a cancellation of polar bonds, that means there's not a dipole moment. So they might be polar, but if they're canceling each other out, then it would be nonpolar. Okay? So the first one we have is HCl. So hydrogen chloride could be one way to say that name. What you could do for this is you could look up their electronegativity numbers, but those don't actually match every single thing that we will talk about. So the way that I did it was I drew a Lewis structure, which again, we did this in Chem 1. We haven't talked about it yet this year, but it has to do with the valence. Do you guys remember, like, hydrogen has 1 valence, so you put 1 dot. And chlorine has 7 valence, so you put 7 dots. Does anything like this look familiar to anybody? Yeah. Okay, and then the bond between them is when you connect the 2 dots together from the 2 different atoms. Okay, now when you draw a Lewis structure, it's kind of really easy to see which side's negative and which side's positive, right? So which of these 2 is the negative one? The chlorine. So you could label that as slightly negative, and then the hydrogen could be the slightly positive. But if you didn't know how to do the Lewis structure, you could just look at their position on the periodic table and how chlorine is very far right. So that means that chlorine is going to be more electronegative, more negative in general than the hydrogen would be. So because there is that difference, then we could also estimate what's the negative and what's the positive side. So if we're going to say that they're positive negative, that means that yes, it does have a dipole moment. So to show the direction, is our arrow going to point to the chlorine, or is our arrow going to point to the hydrogen? To the chlorine. So the dipole moment arrow would point towards the chlorine from the hydrogen. Okay? So that's the first one. Now the next one, we have Cl2. Do you think it's going to have a dipole moment if they're both the same? No. It's going to, just like electronegativity, the numbers would be the same, it subtracts to 0. That's nonpolar covalent. Or if we did draw the Lewis structure, it would be the same. So there's no dipole moment for the Cl2. Okay. Next, SO3. Now the sulfur and the oxygen are in the same column as each other. And I did this earlier. I did look up their electronegativity values and I subtracted, and it equaled 1, which is in the polar covalent range, but it's not polar covalent because of this table. This right here in the table, this example is SO3, which is what we're talking about. And with the SO3, the molecule is what's called trigonal planar. You're going to have to know that by the end of the chapter, where like the S is in the middle and then the oxygens separate themselves evenly. And so for those, every single dipole moment cancels itself out because they're equidistant spaced in a three-dimensional shape. Okay, so no dipole for also the SO3. It's because the molecules and the bonds are exactly 120 degrees apart, so they cancel each other out because that would be shared equally. Okay, and I know thinking about three things is hard to think about shared equally, but we'll talk about bond angles this chapter too. Okay, and the last one that we have is H2S. That we need to figure out if it has a dipole or not. Hydrogen and sulfur, are they close to each other on the periodic table? No, hydrogen's all the way on the left side, right? So sulfur is pretty far away. So that's a hint that yes, it will have a dipole. Okay. I'm just going to move here so I have more space. So this is for the H2S. This will have a dipole. So we're going to connect both H's to the S. Okay. And will the hydrogens be the slightly positive side? Yep. Because usually hydrogen is, there's no way that it's going to be negative most of the time. Okay, so then that means that the slightly positive side, or the slightly negative side, is the sulfur. Okay, so are we going to draw our arrows pointing to the sulfur or to the hydrogens? Both arrows will point to the sulfur. Yep. Probably should have changed colors. Sorry. That might make it easier to see. Okay. So hopefully I did an okay job trying to explain that to you. But this is just another way that even though we're not technically using the numbers from electronegativity, you can still use the thought process behind that to help you predict something like a dipole moment. Okay? If you need more help, let me know. There are cases where it's difficult to determine whether the bond is polar covalent or ionic. Hence that range where it says in your table on the front page of your notes where it says it could be polar covalent or it could be ionic, not in the middle. So there is evidence that there's probably no totally ionic bonds between discrete pairs of atoms. Experimentally, do you need to know this for sure? No on the AP exam, but that's like more high level chemistry. But a great example of this would be ionic compounds that contain polyatomic ions. This was a question we had last unit where on a quiz I said, is like if you have SO4 sulfate ion, I said, does that contain ionic or covalent bonds? Just by itself, SO4 contains covalent bonds. But if you have like sodium sulfate, so Na2SO4, by throwing in the metal, that makes it now an ionic bond between the sodium and the sulfate. There's still the covalent bonds happening in the sulfate, but now the bond between the sodium and the sulfate is your ionic part of that. So technically, the correct answer would be all the bonds involved are both either ionic or covalent. Okay, so that's a great example of how you can be iffy sometimes, but we'll just kind of generalize it. It's important to remember that all polar bonds have some ionic character, and the difference between the ionic and covalent bonding is not distinct, but rather a continuum. So they're very, very similar. Sometimes it's hard to tell the difference, sometimes it's not. So to generalize things, is so that we don't have to worry about electrons or anything like that, we can just say that ionic compounds are ones that conduct electric current when they are melted. Now, are we going to be able to melt any ionic compounds in here? No, because you have to get it to a very high temperature. This is a picture of molten sodium chloride and the light bulb is lit up, so it's indicating that it's conducting electric current because the light bulb's burning up. But melting points of ionic solids are extremely high, like in the 500s plus degrees Celsius. And so we won't be doing that in here, but in some labs they can prove that. Okay, so an easy way without electronegativity to determine if a type of bond is by what type it is by looking at if it has a metal, which we did this in Chem 1. This is our general way of identifying. So if it contains a metal, then it's going to be ionic without fail, as long as it's a metal with another non-metal. But then if you have two nonmetals involved in a bond, then that's definitely covalent. So in general, the best way to characterize the type of bonding is by examining the properties, but this is a good, easy way that if you don't have electronegativity numbers, you can still figure this out. And this is what you did in Chemistry 1, so it should not be a big deal. Okay? Ooh, that had a transition. Okay. Bonding in metals. So, typically metals have different properties such as malleability. Can you change the shape of it? Ductility means can you pull it into a long wire, or can it conduct electricity? So these properties indicate that bonding in metals is both strong and non-directional, meaning that even though it's difficult to separate metal atoms, it's relatively easy to move them around, provided that atoms stay in contact with each other. So the way that we have described these properties of metals and what it has to do with the actual atom of the different types of metal is by coming up with this C electron model, where the valence electrons are delocalized, meaning that they are free floating around and not associated with any individual atom. So in these pictures that I have up here, the pluses, whether it's for the A picture, the +1 or the +2 in the B picture, those would be the nuclei of the metal atoms. And then the space that's kind of pinkish with the electrons noted, that is that delocalized area where the electrons aren't going to stick with their nucleus. They're going to be able to move around freely just within that area where all the nuclei are. Okay? Okay. So a more detailed view of electron energies and motions is called the band model or molecular orbital model. We actually won't get very much into this. This used to be on the AP exam and they took it off. But this model assumes that the electrons travel around the metal crystal in what are called molecular orbitals that are formed from the valence atomic orbitals. And we will talk about the sigma and pi bonds where these orbitals are at the end of the chapter. When many metal atoms interact in a metal crystal, the large number of resulting molecular orbitals become more closely spaced and finally form a continuum of levels called bands. Which you can see the bands in this picture over here. Do you see how there's all these like horizontal lines? I know it's kind of hard to see from far away, but those horizontal lines are evidence that we have these bands from looking at an individual crystal of a piece of metal. And that's it. That's the end.